Hey everyone, and welcome to today's Explainer. Today we're literally decoding the incredible physics that power our modern lives by unpacking the core concepts of alternating current. We're going to be walking through the fundamental forces that light up our cities and run all of our devices. So think about this for a second. Why does almost all the electrical energy we use in our daily lives, the power currently running your screen, your lights, your appliances, why does it come to us as alternating current rather than direct current? Well, the answer lies in a brilliant bit of physics that lets us manipulate electricity for highly efficient long-distance travel. Here's the roadmap for this chapter's explainer. We'll quickly cover 1. Welcome to alternating current. 2. Meet the circuit components. 3. The series LCR circuit. 4. The magic of resonance. And finally, 5. Transformers and the grid. Let's dive in. All right, Section 1, Welcome to Alternating Current. Let's look at the history and the basics. We really can't talk about AC power without talking about Nikola Tesla. A Serbian-American scientist and inventor, Tesla conceived the revolutionary idea of the rotating magnetic field. This concept is the absolute basis of practically all alternating current machinery. By inventing the polyphase system of AC power and the induction motor, he quite literally helped usher in the age of electric power. In fact, his impact was so profound that the standard unit of magnetic field is actually named in his honor. So, what exactly is it? Well, alternating current, or AC, is a voltage and current that vary like a sine function with time. Unlike direct current, or DC, which flows in one steady, continuous direction, AC is constantly oscillating. It's moving back and forth. This sinusoidally varying potential difference is universally used as the standard electric mains supply in our homes and offices today. Moving right along to Section 2, Meet the circuit components. Let's meet the key players. But before we introduce them, we need to demystify a tool we use to analyze them: the phasor. You're going to see this term a lot in physics. A phasor is simply a vector which rotates about the origin with a specific angular speed. Even though voltage and current are technically scalar quantities, these rotating arrows let us easily analyze and represent these sinusoidally varying AC waves. It's really just a fantastic visual shortcut to understanding oscillating energy. Okay, first up is the pure resistor. When we apply an AC voltage to a resistor, it has a very straightforward personality. The voltage and the current reach their zero, minimum, and maximum values at the exact same time. They are perfectly in phase with one another, making it a highly synchronized relationship. Now, our next two components behave completely differently from the resistor, and, well, from each other. In a purely inductive circuit, the inductor actually resists changes in current, which causes the current to lag the voltage by 90 degrees or a quarter cycle. But contrast that with a purely capacitive circuit. The capacitor fills up with charge, which actually causes the current to lead the voltage by 90 degrees. They have entirely opposing phase relationships, making them perfect counterweights to each other. Which brings us to Section 3, the series LCR circuit. It's time for combining these components. Here is the big question that drives this whole chapter. What happens when we take a resistor, an inductor, and a capacitor and wire them all together in series? Basically, what happens when these three entirely distinct component personalities are forced to share a single AC source? Well, they combine to create what we call impedance, denoted by the letter Z. Impedance is the total combined opposition to the alternating current in an LCR circuit. Because the inductor and capacitor are out of phase by 90 degrees in opposite directions, we can't just add their resistances together normally. So the absolutely crucial point here is that we have to use the Pythagorean theorem to calculate this total impedance. We're mathematically combining the standard resistance with the opposing reactances of the inductor and the capacitor. Okay, Section 4, the magic of resonance. Let's look at some fascinating LCR circuit phenomena. To truly grasp resonance, let's look at a highly relatable example. The swing analogy. First, think of pushing a child on a playground swing. That swing acts like a pendulum, right? It has a natural frequency for swinging back and forth. Second, if you push the swing at regular intervals that match this exact natural frequency, you build incredible momentum. And third, because you're matching the natural frequency, your pushes create a massive amplitude, making the swing go higher and higher. Now, the exact same physical principle happens in our LCR circuit. The resonant frequency is the specific frequency where the capacitive reactance and the inductive reactance perfectly match and cancel each other out. Remember how we said the inductor and capacitor pull the phase in completely opposite directions? Well, at this one specific frequency, they balance perfectly, matching the circuit's natural frequency of oscillation. And this brilliantly illustrates the mathematical payoff. At resonance, because those opposing reactive forces cancel each other out entirely, the total impedance of the circuit drops to its absolute minimum. At this point, the impedance simply equals the pure resistance. And because the circuit's opposition to the flow is at its absolute lowest, the current amplitude spikes to its maximum possible value. It's just an elegant, powerful moment of physics. Finally, Section 5, Transformers and the Grid. Let's look at real-world AC. So, we established earlier that almost all our power is AC, but why? The core reason we prefer AC over DC is transmission. How do we get this power from a plant hundreds of miles away to your living room economically and efficiently? The answer is transformers. A transformer basically consists of primary and secondary coils wound around a core. In a step-up transformer, there are more turns in the secondary coil than the primary. This steps the voltage higher but results in less current. Conversely, a step-down transformer has fewer turns in the secondary coil, meaning it outputs lower voltage but higher current. Assuming a well-designed transformer, the power input roughly equals the power output, with efficiencies often exceeding 95%. Pretty amazing. And this represents the absolute genius of the modern AC grid. Power companies use transformers to step up the voltage to incredibly high levels for long-distance transmission. Why? Because high voltage and low current dramatically minimize the energy lost as heat over hundreds of miles of wire. Then, once that electricity reaches your local neighborhood, step-down transformers step the voltage back down to 120 or 240 volts, so it is perfectly safe to use in our homes. We can just change voltages at will. I want to wrap up our explainer on this chapter with this really fantastic thought from the text. Whenever we tune our radio to a favorite station, we are taking advantage of a special property of AC circuits. That's right. Turning a dial on an old radio is literally just manipulating an AC circuit, usually by changing the capacitance, to find that perfect resonance frequency we talked about earlier. You are mechanically matching the natural frequency of your local circuit to the specific frequency of the radio station broadcasting in the air around you, allowing that specific current amplitude to spike and be heard. It kind of makes you wonder, what other invisible waves are you tuning into right now? Thank you for joining me on this explainer today. Keep wondering, keep looking at the science around you, and keep learning.